In this video, we are looking at empirical probability. If our sample is representative of the population, then we can also interpret a percentage we calculate from a contingency table as a probability or the likelihood that something will happen. So we're going to practice that with this contingency table. Example 2 says, contingency tables are frequently used in medical research to assess the performance of diagnostic tests. Suppose 100 healthy individuals and 100 individuals with a particular disease are given a new medical test, and we obtain the following results. You'll notice that this contingency table is not quite finished because we're missing the totals. So we'll start by filling that out. I want you to notice that with a contingency table, the rows will be added together to give us our total for that row. So 87 plus 13 gives us 100. 12 plus 88 gives us 100. And then the columns get added together to give us our totals for the columns. So 87 plus 12 gives us 99, and 13 plus 88 gives us 101. To get that final one, we can add up either the column or the row. Either way, we should still get the same number of 200. Now we can go with probability. Once again, the probability is the same as the percentage. As long as our sample is representative of our population, we're just finding percentages, which essentially is the probability. It says, what is the probability that a randomly selected individual tests positive for the disease? Well, we need to know the number that tested positive, and we'll divide that by the total. In this case, we have that 99 people tested positive, and there are a total of 200 individuals in this study. 99 divided by 200 gives us about 49.5%. Given that an individual tested positive for the disease, what is the probability that they actually have the disease? This is referred to as the precision of the test. Given that an individual tested positive is our condition, so that narrows down our sample, but we're looking for people who have the disease. So we're going to narrow down our sample to the individuals who tested positive. So I'll start by highlighting those people. And we want to find the number of people who tested positive and have the disease. And we'll divide that by our new total of the smaller sample size, which is the total number of people that tested positive. So that gives us 87 divided by 99, which is approximately 87.9%. The next question says, what is the probability that an individual who does not have the disease tests positive? This is the false positive rate. This also has a condition to it. Our condition is the people who do not have the disease. So we're looking for people who tested positive but do not have the disease. And we'll divide that by the total number of people who did not have the disease. So I'll start by highlighting that smaller sample so that we can narrow down our focus to the number of people who do not have the disease and find how many of them tested positive, which happens to be 12. And we'll divide that by the total number of people who did not have the disease, which is 100. 12 divided by 100 is 12%. The next question says, what is the probability that an individual who has the disease tests negative? This is a false negative rate. Once again, we have another condition. Our condition is that we're looking at people who have the disease. So we've narrowed down our sample size to the people who have the disease, and we're looking for those that tested negative. I'll start by highlighting the people who have the disease. And it looks like there are 13 that tested negative who have the disease, giving us 13%.